Okay, so we've saved some time for questions. I just want to make a kind of a final comment before questions. So we've all worked together, just an incredibly exciting area, something that I just continue to be excited about, even though I can't actually do it anymore in my current administrative role. But I just realized this morning when I was thinking about this, if you start with Larry Smarr's PhD thesis in 1975, so it's been roughly 50 years since that time. Turns out I came here, not here in Hamburg, but in Mannheim at Supercomputer 97, and I gave one of the opening keynote talks on the status of the field. So it's kind of like a halfway point through that. And so now we're here to update you on what the great progress has been. And it is really, really exciting. And it's not just about gravitational physics, but as you can see, it's really branching out into all kinds of other areas. And it's just, to me, unbelievable. So why don't we take a pause and see if there are any questions? I hope so. Or we have mics here, I'm sorry.
Jack Wells, NVIDIA. On the AMR, how well did you learn that you needed to conserve energy momentum in order to have a faithful representation? That's one question. And relative to the multi-messenger astrophysics, how quickly can you reorient the other observatories?
Who want to answer the first one, Luciano, or others?
Right, so actually we try to use conservative methods, which means that by construction they conserve rest mass. Angular momentum is definitely harder, but normally the precision that we impose ourselves are below 1% precision, because otherwise you cannot rely on faithful gravitational waves. Gravitational waves are driven by the loss of angular momentum. About the forecast, I think, well, that depends very much on what is the response. If satellites are available, they will be able to react within a few minutes, yes. I don't think seconds, but minutes they would certainly be able.
In the ground-based observatories?
So I think there are two things. For the neutron star detection, the first one, what happened there is that, because it was unexpected, Fermi has an all-sky camera. So it doesn't matter where it happens, it's going to catch it. Now, if you have like maybe a minute or so to steer your telescope and see it, you're going to see still a good portion of the emission. And it's going to be very important to pinpoint the location, because with gravitational waves, it is lousy. So even if you miss the first few seconds, which we hope that doesn't happen, but if it happens, we still be able to see with Fermi where it is, and then to steer the other telescopes within a few minutes to see the rest of the light.
I'd just add one point to that. So the gravitational wave detectors are not really very directional. So you need a network of them, and then you can triangulate the signals in order to pinpoint the direction. And so right now, we don't have very good directionality, but when a new detector comes online in India, that will improve it dramatically. Another question? We have one more. Come on up.
5 seconds.
I'm Tom Gibbs from NVIDIA. The example you gave, Luciano, when you had the one image and were trying to figure out what it was, if you had multi-messenger astrophysics in play, so you had different assets with different views with different spectra, would that have helped you to sort out what that was?
Yeah, so that's a good question. When you do imaging, you just have that image at that very precise frequency, and that's all you can decide. That's why our results have been announced on the basis of that image. But these sources have been observed also at other frequencies. They are observed contemporary to the radio, also in other frequencies. And that allows you to impose other constraints. For instance, one, I mentioned that we can't tell the spin. But in M87, we know that there is a jet, and we know what is the power of that jet. And if you use that information as a prior, then all of a sudden you realize, okay, non-spinning black holes are not allowed, because they will not be able to produce the power in the jet that we observe. So if you stick to the image only, then you have degeneracies. If you start slotting in other information, then these degeneracies are reduced, and that's, you know, the whole art of doing astrophysics, putting in as many pieces of information as possible and prune all the possibilities to a few which you consider to be compelling.
Thanks. One last question? In case there might be, I just want to have one last comment as well. I think it's really important to take this lesson away. This is an area of science that required really sustained long-term investments to help different parts of the community work together over decades in order to make these discoveries. And I think it's a great story, and it's going to keep going. So thanks a lot.